Let's start with a tiny, well, I could have shown the cucumber. It was easier because it is not in the PowerPoint. Okay, so here is what is in PowerPoint. And the initial size can be as small as you want, and then later, after inflation, it becomes as large. Okay, this is just in one particular theory. This is a number of zeros, and what is interesting about it, that these answers remain right in any system of units, in centimeters, in miles, in whatever. This just means that with the accuracy with which we work, centimeter is equal to mile. Okay, no, but no kidding, we are living on the surface of this thing, and we are seeing only a tiny part of it, and all of this part, well, this part looks very, very homogeneous. So that's the basic idea of inflation, but this is called inflationary universe, and now comes inflationary multiverse. So let's just take a football, okay? So instead of a red ball, which, well, reminds me where I came from, now you have this universe multicolored, okay? Tiny, tiny initial ball with black and red and white pieces, etc. And then you have a little bit of inflation, and it becomes huge. And now somebody is going to live in this blue area. He will open his eyes, he will look around, he will see everything is blue. And then he will try to, well, create a theory which explains why it must be blue. Because, yeah, I see it blue, so it must be blue. There must be some physical explanation for that, for blueness. Blueness is the best. Now, those who will live in the red, they will look around and say, I live in the red. Okay, so they are naive. There should be better perspective. I call it cosmopolitan perspective. So it's like, you know, it is called multiverse, but it is just a magic word. Essentially, it's like having universe consisting of different countries. But these countries are so large that you can never travel. There will be never police officers standing. Oh, okay. You do not need anybody because the size is so large that the other country is totally protected from your influence. That is what you live here, and this does not depend on what's happening anywhere else. So it's total peaceful coexistence because nobody cares about nobody else who lives somewhere else. Okay? So that is this inflationary multiverse, and the magic of many universes here is reduced. It's just many different countries. Now, pessimists will say that it is, if each part of the multiverse is so large, we will never see its other parts, so it's impossible to prove that this theory is correct, right? You cannot see this red, blue, whatever, then you say, oh my God, this is just a metaphysics, right? This is why I start with metaphysics. Okay. But then optimists will say, if each part of the multiverse is so large, then we'll never see its other parts, so it's impossible to disprove it. Okay, so same story, but now we should understand, try to understand, what is the generic picture? Generic picture. If you would like to say that our universe is red, then you must have a reason why it must be red, but not blue, not white, not anything else. And then this burden of proof is on your shoulders. Because generically, it can be any. And just look at, well, this analogy. Suppose you are, well, a person who knows, well, what's water? Water can be, it's the same chemistry, H2O, right? But it can be solid, it can be liquid, and it can be vapor, right? And imagine the captain of Titanic who is, well, taking his ship and believes that water can be only liquid, okay? We know how it ended. So, but on top of this, what we learned during this development of inflationary theory, what we have learned, that even if you start with single-colored universe, then quantum fluctuations make it multicolored. And we do not know whether these quantum fluctuations are really powerful enough, but what we do, what we start with just, well, studying how these quantum fluctuations are generated. And this guy is supposed to jump. Okay, so now look at me. Okay, so here is a hill. Okay, so you expand the hill. Yeah, technology, but you have some live entertainer, right? Okay, so you have this hill, and then it stretches in all possible directions. On the top of the hill, new hills are produced, and the universe stretches them on all possible directions. And then new hills on the top of the new hills. And then we have some hills which are extremely large, actually. And there are some hills which are tiny and small. We live in a part of the universe where these hills are low, and we look around, and we see these inhomogeneities in cosmic microwave background radiation. We see these galaxies, and these galaxies have been produced, well, due to this process of enhancement of these quantum fluctuations. But there are also some very, very high peak where these quantum fluctuations by chance overlapped and became very large. So then these parts of the universe are the places where the universe expands very, very fast, and inflation reproduces itself. So you start sitting on this wall, okay? And you're falling down along this shape, parabolic shape of the potential. But occasionally you jump higher. It's very improbable, but occasionally you jump high again. And in those places where you jump, you're rewarded by exponentially large volume, okay? So this resembles your, well, a real situation in our economy. There are not so many billionaires in the United States. Their number probably is growing. But the number, the amount of money which each of them earns has growing exponentially. So the chance that you are a billionaire very, very small, but they have lots of money. So here is the same thing. The chance that the scale field jump high enough is very small, but if it jumps, you're rewarded by exponentially rapid expansion of the universe. Inflation restarts. So this is what we call eternal inflation. Theory of inflationary perturbations was developed, in fact, simultaneously with our development of the basic of inflationary cosmology. It was very, very complicated, and there are two different types of perturbations. One type of perturbation is the perturbations of density, which bend the universe in one particular way. And another type of perturbations is, well, gravitational waves. We squeeze the universe in different directions. So both of these types of perturbations are under active search right now experimentally. And this, by the way, these gravitational waves was essentially predicted even before inflation was predicted, because the mechanism is so generic that it works in a very broad class of models. What do you do in order to test it? Well, you go to Florida, and then you watch the satellite launch, and then you just watch what happens there. And if you look at the sky very, very carefully, you will see, oh yeah, of course, from the chair, no, it's hardly possible. Because what they see are, well, measure of fluctuations is like 10 to the minus 5 of 1 Kelvin. That's just incredible. That's incredible. Okay. I never believed that it's possible, but then I learned not to underestimate your experimentalist colleagues. I'm a theorist. What do I know? Okay, so this is a Planck satellite. Planck satellite was launched a long time ago. The project actually was delayed for 10 years, which was a shame. But then eventually it was launched, and then it produced these images of the universe. And I remember one of the PIs, well, the principal investigators of this Planck team, when he have shown this image at the press conference a year ago, he said something like that. Oh my, that was something. Okay, he said, look at this picture. It looks like just a muddy picture, nothing special. But I know some people who would sell their children to get this picture first. So yeah, many people could not forgive them for that. They sent them offending letters. But that's how people were feeling about it. And this is the picture which Alan Guth have shown you, illustrating the progress in this direction which we're able to achieve. So these magic numbers, this omega close to 1, as Alan told you, our, well, expectations of astronomers were that it is 0.3. And I remember how one of them was telling to my wife, who is an expert in supergravity, it's so sad that inflationary theory is finally ruled out. And she said, why? Why it's ruled out? And he said, oh, because I came from the conference in Princeton, and they explained us right now that omega is equal to 0.3, and therefore, unfortunately, inflationary theory is finally ruled out. And my wife said, but Andrei just called me from UCLA, and UCLA, they announced a discovery of, well, this special distribution of supernova, which indicate that actually the total well, density of the universe is close to critical, so everything seemed to be fine. He said, no, I came from a real conference in Princeton, not in UCLA. And they say that this 0.3. But next morning, all walls in his institute were covered by newspapers while announcing this discovery. So yeah, it was pretty dramatic. Anyway, after that, there was this bicep. Bicep story is not finished yet. It's definitely true that, or definitely, well, never say definitely, but definitely true nevertheless, that they have found B modes, and B modes is special polarization of, well, CMB light coming from different parts of the sky. When people say good things or bad things about bicep, whether they discuss what they do, whether it's trustworthy or not, let's remember one thing. They measured temperature of microwave background radiation with accuracy 1 in 30 millions. That's just record-breaking people. They spent years sitting at the South Pole and doing it. Well, we will see what does it mean, because the result is there, but interpretation of results will require further scrutiny. But I'm just saying we should applaud this enormous progress in experimental development, which was totally unbelievable before. This is like an easy summary of what I just told. So we're sitting on the Earth, and we're looking around, and we're using our Earth like well, space travel machine, like time travel machine, in fact. Because when we are looking at our sun, we see the sun as it was several minutes ago. When we're looking at distant stars, we see these stars at 100 years ago, like 1,000,000 years ago. When we go further and we look at galaxies, we can see galaxies as they were existing 2 million years ago, 10 billion years ago, when the first ones started being formed. And then we come closer to this cosmic fire produced. We see this cosmic microwave background radiation, which was dispatched and left and traveled freely from the moment approximately corresponding to 400,000 years after the Big Bang. Okay? So we see this, and that is where all of this information for all of these satellites came from, including Planck and WMAP, and the information from BICEP. This is what they see. But they cannot go closer to the Big Bang because the universe at that time was non-transparent. Non-transparent, just like a sun. Sun is transparent for only several hundred kilometers because the light is scattering in the plasma, and we do not see this light coming from the center of the sun. We can use neutrinos, which come from the center of the sun. That is a direct way of getting information about what is going on, or almost direct, because neutrinos change their nature on the way to us and cheat us a little bit. But then if we have gravitational waves which would come directly to us, not polarization, which is still indirect, but gravitational waves which come directly to us, then we would be able to come very, very close to the Big Bang. And the idea was, here is this cosmic sphere, this is the Big Bang, this is a distance like 14 billion light years ago, and we cannot go any further. And when inflation came, here is what happened. We realized that the universe became hot only after the end of inflation. In inflation, energy was sitting in the scale field. There was no particles during inflation, or if there were any, they were diluted. Okay? So the density of normal matter during inflation was very, very small, and after inflation, the scalar field started oscillating, and when it oscillated, it produced normal particles, and these normal particles interacted with each other, they became hot, so here is your hot Big Bang. Okay? If you call Big Bang the beginning of everything, then, well, this was before inflation. If you call Big Bang as a moment when the universe became hot, yes, this is after inflation. So first was inflation, then there was this hot Big Bang. Okay, so this was a change of perspective. Previously, we thought that here is Big Bang, then everything else. Okay, then the picture became like that. It was slowly changing. Big Bang, hot Big Bang, then the temperature drops down, then you have a period of inflation, and then it is hot again. That was the basis of Alan Guth's theory and of my modification of the theory, which is called the new inflation. But then, in this simple picture with this parabolic potential and many others, all models which we are using right now, all versions of inflationary theory, we really do not need, usually, in 99.9% of the existing models, we do not need any assumptions that the universe originally was hot, that it was created from, well, hot Big Bang singularity, and we do not need any relation with phase transitions, with grand unified theory. People by, they just continue repeating it about grand unified theory, and the energy scale may be close to the grand unified theory. But in fact, the parameters of the model, for example, this quadratic model, they do not have anything with grand unified theory. The field has mass 3 orders of magnitude smaller than grandification mass scale. The field size is 3 orders of magnitude larger than grand unification scale. But just when you multiply one by another and take a square root, you get grand unification scale. You say, oh my God, this is grand unification. Nope, it is not so. It's just grand unification energy scale, that's all. So now we see that we can put our nose outside of it, and we understand what happens. Because previously we thought, this fire, this is the beginning of everything. But in fact, we were just like wolves. We are surrounded by fire, and here's the end of the world, and we were afraid to jump through. Now when we jump through, we see that lots of place here when there was no particles. There was only this energetic scalar field. It's almost like energetic vacuum. It's slightly different, okay? And then if we continue moving further, we will see something else. We will see these parts of the universe where the universe produces itself in all of its possible forms.